So today we're going to take some notes and we're going to focus on using equations to help us solve for future values. So similar to when we looked at constant velocity, we spent a lot of time on graphing and then we went into using some equations to help us solve problems. We're going to do that again today, only now we've got to add a degree of difficulty because our acceleration is no longer zero. So recall when we were talking about constant velocity with our acceleration of zero, we had a position equation of this guy right here, delta x equals v times t. That's valid only when the acceleration is zero. We're going to start having problems now where the acceleration is not zero, so we have to use some different equations. And we have three. We have this equation right here, which we're going to call the position equation. So this is our position equation, because this equation gives us the position or the change in position after some time has passed. So let's take a look at these variables. We remember our good friend delta x, right? That just means change in position, right? How far has something traveled? VI might be a little bit new, that little subscript I there. That's the initial velocity. Because we have acceleration, the velocity is not constant, it's changing. So we're looking at the initial velocity when we hit that stopwatch, that time of zero, okay? T hasn't changed, it's still time. A is still acceleration, okay? We said earlier that A was going to stand for acceleration. And let's go ahead and put some units in here, right? We remember we measure position in meters. We measure time in seconds. We measure velocity in meters per second, and our acceleration is in meters per second squared. Our second equation is called our acceleration equation. So we can call this our acceleration equation. And the variables aren't very different. We have one new one here. So VF stands for the final velocity. VI is still initial velocity, A is still acceleration, T is still time. Since VF is a final velocity, we're still measuring that in meters per second, so nothing too new there. Our last equation is called timeless. So timeless equation, and you'll notice it's called timeless because there's no time in the equation. And there's a couple of really important parts I want you to understand about our timeless equation. Okay, first, let's look at how our final velocity, and we would read this as final velocity squared is equal to the initial velocity squared plus 2 times a times delta x. So be very careful with that squared term. A lot of people like to forget that squared term, and then they don't end up solving for the correct value, okay? Now, just like in our constant velocity problems, we are going to run into some problems that we read, and there's going to be some hidden information. So you might be reading a problem and it might say something starts from rest. Okay, make sure you understand that that means that the initial velocity is zero. It doesn't say the initial velocity is zero, but when you see starts from rest, you will know that the initial velocity is zero. Or you'll read that something comes to a stop or stops. You'll know then that the final velocity must be zero. And when you list out your variables, you'll be able to fill that in. When something moves with a constant velocity, this is like our problems from the last unit, there we have to remember that anytime we have a constant velocity, we know the acceleration is equal to zero. We also know that the initial and the final velocities have to be the same because there's no changing of the velocity. So we can use this and we can hopefully help solve some problems. So let's take a look at a couple examples. If you don't have your calculator out, now would be a great time to get your calculator out. So let's read through this. A car starts at a velocity of 3 meters per second and accelerates to a velocity of 21 meters per second in 6 seconds. What is the car's acceleration? So just like before, I'm going to go ahead and I'm going to list my variables. Only now we have some extra ones. We don't just have three. We've got delta x, change in position. We've got VI, initial velocity. We have VF, final velocity. We have A, acceleration, and T for time. So let's go ahead and list out what we know. It says a car starts at a velocity of 3 meters per second. That meters per second means it must be a velocity. And since the car starts at that velocity, I know the initial velocity must be 3 meters per second. It accelerates to a velocity of 21 meters per second. A lot of people look at this and say, oh, well, the acceleration must be 21 meters per second, but that can't possibly be right just based on the units. We measure acceleration in meters per second squared. This number is 21 meters per second, so this is actually the final velocity, 21 meters per second. In 6 seconds, well, it doesn't give me much of a hint. The problem doesn't give me much of a hint as to what that number represents, but since the units are there, 6 seconds, I know that that must be a time. Our time in this case is 6 seconds. I don't know delta x, and I don't know acceleration, so I'm going to go ahead and put question marks for those. The good news is that I've always got 5 variables for these types of problems, and as long as I know 3, I can always find the other 2. So they're asking for what's the car's acceleration. Well, we remember from last unit, once I've gone ahead and listed my variables and filled in what I know, the next thing we want to do is pick an equation. So we can look at our equations up above. We have 3 equations, and you might think, well, let's go ahead and let's just pick the first one. Why not? Well, let's pick this position equation. And you can go ahead and you can copy and paste it, but I'll just write it down here. Delta x is v initial times time plus 1/2 at squared. And you might see that we've got a problem because there's 2 things we don't know. We don't know delta x, and we don't know a. So that's okay. You picked the wrong equation. This is not something to worry about. This is just something where we're going to go, you know what? Let's try another one. So if that happens to you, you just go, that's okay. I'll just pick another equation. The next one you might try is the acceleration equation. V final is equal to v initial plus a times t. Well, I know the final velocity. I know the initial velocity. I don't know the acceleration, but I do know the time. So I think this equation is going to work just great for us. So final velocity is 21 meters per second. I go ahead and put that into my equation with units. That equals 3 meters per second plus the acceleration times the time of 6 seconds. Hopefully you remember some algebra. The first thing we're going to do to solve for a is we're going to subtract this 3 meters per second from each side. And you're going to get that 18 meters per second is equal to a times 6 seconds. Now I can go ahead and divide out that 6 seconds on each side, and I can see, and I'm going to go ahead and write it over here, that a must be equal to, let's see, 18 divided by 6 is 3. Meters per second divided by seconds, I could write it like this, meters per second, or the preferred method for most students is just to put 3 meters per second squared. There you go. You just did your first constant acceleration, non-zero acceleration kinematics problem. So let's go ahead and take a look at this next problem. It says, use the acceleration you found in the previous question. What distance did the car from problem 1 travel in this time? So, distance did the car travel? I know I'm trying to find delta x. That must be my question mark. I still know some other things about the problem. I still started with 3 meters per second of velocity. I still ended with 21 meters per second of velocity. I know my acceleration now because we found that in the last problem, and I'm still using the same time. So now we have to go ahead and pick an equation, and since we're trying to find how far, I would argue that starting with the position equation would be a great guess. I know the initial velocity, I know the time, I know the acceleration, I still know time. This equation should work. So let's go ahead, let's plug these numbers in. Delta x is equal to, let's see, my initial velocity is 3 meters per second. My time is 6 seconds plus 1/2. My acceleration is 3 meters per second squared. My time is 6 seconds. And remember, this squared means I have to square just the t. So that's 6 seconds is going to be squared. So now I can go ahead and I can do a little arithmetic. 3 times 6 is 18. These seconds cancel with these seconds, so I'm left with 18 meters plus, let's see, I can do a little bit of mental math here. So I've got 1/2 times 3 times 6 squared. So 6 squared is 36. So let's see, go ahead and use your calculator, see what you get. All right, I'm pretty sure we get 54, okay. Now, the units are a little tough. You actually square these units. If we square the 6, we have to square everything inside of this parentheses, which means the seconds become squared as well. So now I can see that the seconds squared are going to cancel with these seconds squared, and I'm just going to be left with 54 meters. So you can go ahead and put that in your calculator. You can see that what are we going to end up with here? 72 meters for our change in position. All right, one more problem, and then you are going to do some practice on your own. So the same car then slows from a starting velocity of 21 meters per second to a complete stop with an acceleration of -2 meters per second squared. How far did the car travel in this time? So this acceleration is now negative. We started with a positive velocity. We're coming to a stop, so we have negative acceleration. So let's fill in what we know. Delta x we don't know. Our initial velocity is different this time. It's 21 meters per second because we restarted our timer. We said we're starting when it's already going 21 meters per second. We're starting the timer right as it starts to stop. Our final velocity, since it comes to a stop, is 0. Our acceleration is -2 meters per second squared, and we don't know the time. In fact, they're not asking for the time, right? So I would go ahead and put a question mark there instead of t. And all I have to find is delta x. Since I don't know the time, and I'm trying to find delta x, I would argue that starting with the timeless equation is probably your best bet. There's our timeless equation. You don't have to memorize those. We'll give those to you on a test. But my guess is that if you've done enough of these problems before the test, you will have this memorized. So let's take a look and see what we got here. V final. Well, V final, even 0, squared is still 0, is equal to the initial velocity, 21 meters per second. We have to square that, plus 2 times -2 meters per second squared, all times delta x. So go ahead and plug that in your calculator and see what you get. All right, when I did that problem, and I'll go ahead and show you a little bit of the math. So I get 0 equals, well, 21 squared is 441 meters squared per second squared. Yeah, we have to square everything on the inside. So the 21 gets squared, the meters get squared, and the seconds get squared. And then I can go ahead and simplify this a little bit. This is going to be minus, because 2 times -2 is negative, minus 4 meters per second squared times delta x. Now I have to bring one of these over to the other side. I'm going to go ahead and bring over this entire term right here, because then I'm going to end up with positive values. And I'm going to go ahead and I'm going to write 4 meters per second squared times delta x is equal to 441 meters squared per second squared. And since I want to solve for delta x, I need to divide by 4 meters per second squared on each side. When I do that, you're going to get some weird units, but or not weird, but tough to determine. These are going to cancel. I'm going to be left with delta x on this side. And when I go ahead and I divide 441 by 4, I get 110.25. Now, what are these units? Let's go ahead. We can take this kind of slow. But remember, I can go ahead and I can rewrite this kind of complex fraction. Right? This is just this value divided by this value. So I could on the side here write 441 meters squared per second squared divided by 4 meters. I'm going to do that. 4 meters per second squared. So I can do a little keep change flip. That's really just 441 meters squared over second squared times seconds squared over 4 meters. Well, look at that. Those seconds squared cancels with those seconds squared. This meter cancels that squared, and I'm left with just meters for my result, which is exactly what I would expect it to be. Delta x is equal to 110.25 if you want to have a lot of significant figures. 110.25 meters. So those are the types of problems you're going to be doing and practicing for today. If you get stuck, check your variables, make sure you listed everything correctly, then try another equation. Good luck.